Hello. As part of Phase 5, I wrote a disassembler, mainly to make my life a bit easier and we could actually start reading things in more human readable form than in the hexadecimal machine code or the hexadecimal representation of machine code. So in this video I thought I'd demonstrate how the disassembler works in practice and how it was implemented. Now this here is memory dump, is what we've been using earlier on to show what's in the various parts of memory, and it was up to us to sort of get it right with the A9 and 7, so what A9 and 7F there is a representation of this here, the LDA immediate. LDA immediate with 7F, and then the 6.9 there is the add with carry, and it's adding a 1. So this series of commands here says load the accumulator with 7F, add 1 to the accumulator, which makes it 80, and then return from subroutine. Actually, this routine was a good routine because the 7F is the last, the highest possible positive number that an 8-bit value, assigned 8-bit value, can represent. So 80 turns it negative, so it's a great way of testing whether the overflow flag works. Anyway, that's for a different video. So we know that from previous videos that the hex code here represents something, and that something is represented by a mnemonic. So in this particular case, it's a logical shift right there, you see, and so therefore that what was it, 446 in hex would be that logical shift right. Well, how do you do this? How do you convert that hexadecimal into something like that's human readable? Well, as it happens, the 6502 instruction set is set up in a particular way, and we'll come on to how it's set up in a minute. But if you rearrange the table, and this website does this nicely for us, we don't have to do it ourselves, and you can rearrange the table in several ways, but this is one of the ways where you have C and A as the rows, and B as the columns. So B being the dressing modes. So if you look here, you can see that most of these, so this is all the implied, this is absolutes, and in some indirects and some other bits and pieces, but mostly absolutes. Then you've got your relatives, and if you go down, you can see that you've got all this other stuff here. It's all absolute still down here. Your immediates, and then your accumulators and your implieds. The funny thing is, accumulators and implieds are still only 1-bit instructions, because if it's implied in the name of the instruction. If it's accumulator, although it's not implied, it's still only 1 byte and there's nothing coming after it. So it's, all these are all 1-byte instructions. So you can look at it that way, or you can look at it this way, and this way is taking the C with the B here, with B being the addressing mode, and then looking at the individual instructions. So that means then that the addressing mode reads left to right, and the instructions work down. Now, if you want to represent that in C code, what you can do is you can put it into arrays, and I've used 2 of them in the disassembler for convenience. I sort of sat down and worked it out which was the best way of doing it, and the quickest and most convenient way for me at the time was to do it this way. So this array here says B where C equals 0, so that's row B where C equals 0, and if you look at those, they line up, and the ones with the triple dots in are the ones we're not interested in, the instructions we're not interested in, so you should never see any of them as part of the disassembly. This here says row C with column A, so that was that second table we looked at. So where C equals 0, these are the instructions. Where C equals 1, these are the instructions. And C equals 2, these are the instructions. And C equals 3, i.e. 1, 1, they're illegal, so you don't bother with them. And the way it's used is dependent upon the type of instruction that you've got. You can you reference a different one of the two arrays but differently. So if, for example, here's the logic, so this is the logic that decides whether or not this is an implied set of instructions, and then to get the instruction itself you actually reference it from there. And same down here, these are the this is basically switched. This switch statement is switched on B, so it's switched on addressing mode type. So if the addressing mode type is 0, then it's an X indirect, and then you use the array of C with row A, because that's what we saw before. Now then, what also we can do, I say what we'll demonstrate it before we do anything else. So if you remember, this is what we saw. So if we disassemble that particular area of memory there, C201 through to, what was it, C205, was it? Yeah. And you can see that this is the disassembly portion, the bit that actually turns the machine code here into assembly language mnemonics here. So now you can actually read it as you would write it into an assembler. Alright, so the way that I designed it, first of all, I used the website there at the top. It's a very good website, and it's got a lot of information. I also used the 6502, the MOS 6502 reference manual. I decided on the data structures, and as just pointed out, the way I decided on those data structures was based upon the tables on the website. The 6502 instruction set is organized, okay, and it's organized in 2 octal bits, which we've referred to here as AAA and BBB, plus 2 binary bits of CC. So that's what that A, B, and C was in the previous example. We'll come more onto that in a minute. So within my disassembler, it's not necessarily the best way of doing it, but I kind of used the I used the addressing modes to kind of keep the code as simple as possible. So this is how it works. I split the opcode into the AAA, BBB, CC notation using 3 variables. So I use the variables A, B, and C because that makes it easy. And then I went through this logical routine here. Is it an implied instruction? Yes or no? If it's no, is it a JSR? Yes or no? If it's a no, is it a branch? Yes or no? And if it's a no, then I can select by B addressing mode, because that's the only thing left. So get rid of all the stuff that it's not beforehand, and then work on the addressing modes afterwards. It seems sort of quite logical to me. So we'll start with the opcode. I take the opcode, in this case we'll take the opcode of DE, and we split it down into 2 octals and a binary. So we end up with 110, 111, 10. And then we put them into the variables A, B, and C. So in this case, A equals 6, B equals 7, and C equals 2. Then we say, is this instruction an implied instruction? So for an instruction to be implied, B and C must be even, so therefore B or C can't be like 1, 3 or whatever, you know, they've got to be 0, 2, 4, 6, so on. And then it says when B equals 0, then A must be either 0, 2 or 3, and B can't be 4. Right, so that's the rules that you would apply to check if it's an implied instruction. Now let's just have a little look here. Is B even? No, it's not. So therefore this can't be an implied instruction. Next. Is it a JSR? Well, JSR only fits a single pattern. That's A equals 1, B equals 0, and C equals 0. And we can see that it doesn't match that either. Is it a branch instruction? Well, branches all fit into the row of B4 when C equals 0. So C does not equal 0, so therefore it isn't a branch instruction. Therefore, it must be an instruction with an addressing mode. It has to be, because that's all that's left. So using B as a selector, because B selects the addressing mode, we say when B equals 0, which is X indirect, this case has a few immediate instructions that you need to check for, and the immediate instructions are A equals 5 and C equals 2, but we don't need to worry about that at the moment because our B does not equal 0. When B equals 1, no it doesn't. 2, no. 3, no. 4. B equals 7. So therefore we know we've found our instruction class, and it's an absolute X type instruction because our B equals 7. So now we move on and we say, okay, what are you? So we use a lookup table, and those two arrays I demonstrated before are our lookup table. This is B rows where C equals 0. Well, our C doesn't equal 0, so it doesn't fall into that one. And this is C rows using A columns. Well, yeah, it does, because it doesn't matter. There is no condition on C there. So our example falls into this. And what we do is we say we display the array with column plus row times 8, and that's just that row times 8 is just a way of representing a two-dimensional array in a single dimension array, which is the way that C actually does it anyway, so I didn't see the point of building a two-dimensional array, which basically says 6, that comes from the A, times plus 2 times 8, and the 2 comes from the C and the 8 comes from here, so 2 times 8 16 plus 6 equals 22, or CA22. So that is the reference of the array. So C underscore A, as we saw before, is the reference, and that would pull out that string there, dec, with a null terminate, and it turns out that it's a dec absolute. So can we check that? Can we check that DE is a dec absolute? And the answer is yes, we can, because the way we can do this is we can actually use our insert. So we can say insert, and we'll just choose an arbitrary address of 500 DE, and then we'll insert at 500 again. Now we knew, sorry, 501. Now we knew that it was an absolute with an X index. So absolutes are 3 bytes instructions, aren't they? So we've already put 1 byte in. So let's put another byte in of AA, and then we'll put in insert for 502 of BB. Little endian, remember. So that should say decrement whatever's in BBAA by 1. So if we do a disassemble on that now, when we say disassemble 500 through to 502, we can see that we have got the decrement BBAA, and that's precisely what we expected to see because of the way that the decode works. And if we go and have a look at up here, we can probably work that out from the from this instruction set here. Look, there we go, there's our decrement here, and if we were to work that out, what did we say it was, 22 or something? Well, C array starts at 0, so 0 through to 7, that makes that 15, that makes that 16, 17, 18, 19, 20, 21 and 22, which is the dec instruction. So the question is, does it actually act like a dec instruction? Does it work? Does it decrement the accumulator? Well, if we display the registers just to be on the safe side, and we have a look, our accumulator is A. Now bearing in mind, to decrement 0 you'd end up with -1, but the representation for -1 on an 8-bit accumulator gives you FF in 2's complement, does it not? So if we say step for 500, there we go, and we should end up with, sorry, not the accumulator, is it? It wasn't playing with the accumulator, it was playing with BBAA, wasn't it? So if we now go and have a look at BBAA, we can now see that FF is in there because there was a 0 in prior, but we can do it again. That should, you know, if we actually ran that piece of code again, so 500, what would we expect to see in there? So if we have a look at memory of BBAA, should we not expect to see FE in there? And we do. So that decrement instruction works. So not only does it work, we knew it worked, we knew that our code for decrement worked because I've tested that before. So we now know that our disassembler represents DE as the decrement, and that means that the disassembler is disassembling that piece of code correctly, because if it wasn't, it would have done something that we didn't expect. So that was a pretty good test for that disassembler. Okay, so this is just a quick walkthrough now. From the slide, we saw that the first thing we did was we split the we split up our our opcode into A, B, and C, and that's precisely what we're doing there. We're splitting that opcode up into A, B, and C. All right, so into the two octal parts and the binary pair. Then we're checking for immediate implied instructions, and this is the logic that goes around that, and you can see it's quite convoluted, but it's pretty straightforward in real terms, because what you're actually saying was what we went in there. We said is C equals 0 or C equals 2, and whatever, all the B's and the A's. So we followed our logic perfectly well, and that's what puts it in, and then it checks for specifics for C equals 2 and B equals 2, because if all this is correct, then all we have to do is check for this, and then we print it in that format, because these are the funny instructions at the end that I cheated slightly. Well, I say cheated, but I actually put all the weird sort of 1-byte instructions and things at the end, all the TAXs and all of that, because they're although they're not actually, although they are implied instructions, some of them aren't. For example, that ASL there, arithmetic shift left, well, that's not an implied instruction, that's an accumulator instruction, but it's the same thing. It's 1-byte instruction. And if it's not that, then it must be one of these. So that's pretty much how that works. Then we do exactly the same thing as we did. We check whether it's a JSR, yes or no. And if it's not a JSR, is it a branch? Yes or no. If, else, no, right? So therefore, if it's not a branch, then it has to be everything else, and everything else happens to fall into the addressing mode category. So therefore, check for the case on B, case 0, 1, 2, 3, 4, 5, 6, and 7, and that 7 there is the absolute X, which is where our instruction fell into. Now, I did write an original version of this disassembler, which was a lot of rubbish. And the way it worked was it just used a switch case statement, and it just put a case in for each and every opcode, and then printed out the relevant line, which was kind of ham-fisted and hackish. It's also a really good example of how not to do it, because it's full of bugs, and the problem is I copied and pasted the bugs from one line to another, so actually fixing this was kind of like complete nonsense. So I left it in here to demonstrate the best way of not doing something, and the reason why you should check stuff before you do copy and paste, because you end up copying an absolute load of bugs, because it didn't do little endian representation for a start, and some of the instruction decode was wrong. So I left it here just to sort of show you that's where I started off, and I didn't like it. I didn't even want to debug it. I just thought it's rubbish. So I actually wrote something a little bit better, in my opinion. It's a little bit more difficult to read. I agree. I understand that, but I think it's better code. It's certainly more flexible code, and it's certainly more in keeping with the way I think that the 6502 works. I think there's probably a slightly better way of arranging the arrays within here, but I think I'll leave it alone for the time being. It looks okay to me. So that's pretty much how a disassembler, what a disassembler does and how it works. I might write an assembler, I might not, because there's some good 6502 assemblers on the market. But as it stands at the moment, this is as far as I got now, up to this point with the emulator. The next phase is deciding where I'm going from there.